When a massive industrial motor is spinning at full capacity, it pulls thousands of watts of electrical energy from the grid to do physical work. But occasionally, a grid will experience a silent failure. The regional transmission lines begin to overheat with excessive current, and the local voltage drops to levels too low for the machinery to function. The paradox is that the power plant miles away is still generating plenty of real power, the actual wattage required to keep the machinery moving. Yet, the motor begins to stall, and the local grid approaches a blackout. The stability of an alternating current grid relies on mathematical forces entirely separate from the consumption of raw energy. It is dictated by the behavior of two foundational passive components, inductors and capacitors. These devices technically consume zero real power, but if engineers fail to manage their effects, the entire transmission network will succumb to a total voltage collapse. A capacitor is simply two conductive metal plates separated by an interleaving layer, known as a dielectric. As electrons accumulate on the plates, it stores energy in an electric field. The stored charge, Q, is directly determined by the applied voltage. Because electrical current is the measure of how fast that charge is moving, the circuit's current is defined by how fast the voltage changes. This creates the governing equation: current equals capacitance times the derivative of voltage over time. Mathematically, this means current can only flow through the circuit when the voltage is actively changing. The current reaches its absolute peak precisely when the voltage curve is at its steepest slope and changing the fastest. When the voltage reaches its peak and momentarily stops changing, the derivative drops to zero. At that exact millisecond, the current flow also stops. This derivative relationship forces the current wave to shift horizontally. In a capacitor, the current will always peak before the voltage does, leading it by exactly 90 degrees. The physical barrier of the insulator creates a circuit where current and voltage are permanently locked out of sync. The mathematical mirror to a capacitor is an inductor, which is physically just a piece of conducting wire wound into a coil. When current flows through this coil, it generates a magnetic field in the surrounding space. This stored magnetic energy fiercely opposes any change in the current passing through it by inducing a reverse voltage, or back EMF, across the coil. This chart models an inductor, where the differential equation is inverted. Voltage equals inductance multiplied by the derivative of current over time. Here, the voltage relies entirely on the rate of change of the current. When the current is rising or falling at its fastest rate, the induced voltage hits its maximum peak. As a result, the phase shift is reversed. In any inductor, the current wave will always lag behind the voltage wave by 90 degrees. Inductors and capacitors behave as exact mathematical opposites. One reacts to changing voltage by generating an electric field. The other reacts to changing current by generating a magnetic field. This symmetrical dualism governs all alternating current behavior. This visualization overlays voltage and current, multiplying them together to plot a third wave, electrical power. Because the voltage and current are pushed out of phase, there are periods in every cycle where the two values have opposite signs. A positive multiplied by a negative results in a power wave that dips below zero. We call this reactive power, measured in volts-amperes reactive, or VARs. This is energy that simply pulsates back and forth between the magnetic and electric fields without doing any actual physical work. When we zoom out to the macro scale, the impact of this pulsating energy becomes a severe engineering problem. Industrial environments, like manufacturing plants and pumping stations, are dominated by heavy machinery. Physically, these large electric motors are just massive inductors. To maintain the immense magnetic fields required to turn their drive shafts, these motors constantly pull a massive supply of reactive power from the grid. If the distant power plant supplies these VARs, this useless pulsating reactive current has to travel for miles across the physical high-voltage transmission network. This vector diagram maps the consequence. As high levels of reactive current pass through the natural resistance of the transmission line, it creates a severe voltage drop by the time it reaches the factory. If the voltage drops to a critical point, the grid enters a state of voltage collapse. The grid attempts to serve heavy loads with unstable voltage levels, causing local equipment to stall, overheat, and trip circuit breakers. Generating an abundance of real power is useless if the unchecked demand for reactive power crushes the transmission voltage before the energy ever arrives. To stop voltage collapse, engineers have to address the factory motor's desperate need for lagging VARs to maintain its magnetic field. The solution relies on physical placement. installing a static capacitor bank directly next to the inductive motor on the factory floor. The physics of the two devices interlock. The inductor produces energy during the exact half-cycle the capacitor absorbs it. The capacitor provides leading VARs perfectly tailored to satisfy the motor's lagging VARs. They trade energy back and forth locally, requiring zero reactive power from the grid. Immediately, the regional transmission lines are cleared of the pulsating reactive current. With the excess current eliminated, the resistive line losses decrease, and the local voltage returns to its required rating. By pairing the mathematical opposites of inductance and capacitance at the point of consumption, engineers isolate the reactive power and neutralize the threat of voltage collapse. On a national power grid, this local balancing act is monitored and repeated millions of times across the continent. Grid stability requires maintaining a constant equilibrium between electric fields and magnetic fields across thousands of miles of wire. Success is measured by maintaining a perfect 1.0 per unit voltage profile, pushing steady electricity through the fluctuating demands of modern society. Sustaining a modern grid requires a mastery of the invisible mathematical pressures that keep voltage levels stable enough for power to reach its destination.